Lifetimes. Lifetimes are actually a feature of every language. The idea that a reference to a value has a amount of time where it lives. After that, the memory is freed, or at least might be overwritten, and so it's not safe to access that value anymore. It's not safe to follow that reference anymore. Some languages handle this in various ways. Rust doesn't have a garbage collector. Instead, it figures out the lifetime. The borrow checker figures out the lifetime of all the variables you're using, all the references you're using, and ensures that references live long enough and that values aren't possibly overwritten during a time where they might still be referred to. So all of that to say, everything has lifetimes, whether you know it or not. The compiler can usually figure out automatically what the lifetimes are, but sometimes we have to give the compiler hints, and that's what this lesson's about. Lifetimes do kind of complicate the code. There's a good reason why we don't specify all the time, because they'd be everywhere. They'd be attached to everything. Every single variable, or every single reference at least, would have a lifetime attached to it. Here's an example of a function that gets a lifetime attached to it. First, this is just a normal function declaration. You're used to this. I've used these filler names. There's a function name, and then you have an argument, any number of arguments in here, and the type that argument is, and then you have a return type. Well, if we were to add lifetimes here, this is how you do a lifetime specifier. You might recognize the angle brackets from when we use generics. If we specify generics, they're going to go here too. For example, if we're using type T. There's a lifetime specifier, and we can name this anything we want, except for a few reserved lifetime names like static, which you'll have to look at the text portion to understand. We're not going to talk about this in the video. Except for that, there are no restrictions on naming lifetimes, and it's convention to name them A, B, C. But for example, I could do T here to match type. If you use cert deserialize, you'll notice that it uses DE because it's deserialize, and so it uses that lifetime. So this lifetime indicator here there's something magical about it being A. We just named it A because that's the first letter in the alphabet, and we're distinguishing it from B and C. But we could name it pretty much whatever we want. And so this A lifetime here is telling us that there is some amount of time that is called A. And the things that live in A they live with each other in A. In other words, we have this type, whatever it is, we have a reference to it that has lifetime A, and we're telling the compiler here, we're not changing the lifetime here, we're just informing the compiler how things work. We're saying that this returned reference lives also with lifetime A. It lives for the same amount of time as the argument here does. And we're hinting to the compiler because we've written code that's too complex for it to figure out otherwise. If all of that sounds terribly annoying, it is if you're coming from another language, and lifetimes do take some getting used to, but thankfully we don't usually have to use them. In this example here, I have a getOwner function where I have this A lifetime, and I say that this account that I'm pulling in, I return a string, and it has the same lifetime as the account. The compiler isn't aware that the owner of an account would necessarily live as long as the account itself, right? So we tell the compiler that. This would generally be unnecessary, especially since string is an owned value. If we just returned string here, rather than a reference to string, we return an owned string, then the compiler can figure out everything, and we don't need to specify lifetimes at all here. And of course we do this, or toString or something. We can get rid of lifetimes by returning owned values. So you don't have to work with lifetimes. And primarily I'm introducing them even in this basics course because you will see them. And you'll see them in places, especially classes. We'll get to that in a second. But if we did use a lifetime here, what's going on is we're tying, again, the lifetime of this input reference to this returned reference and saying, hey, this string I'm giving back, it's not going to outlive a count. You can free up that. You can consider that reference invalid. At the same time, the reference of this input account is invalid. Learn is brought to you completely free because of our great sponsors. Neutron, enabling developers to build breakthrough applications and onboard users from anywhere. Osmosis, the premier decentralized crypto exchange. And Obi, the smart new standard for asset management. If you want to become a smart contract developer through this lesson and others like it, head to heretolearn.xyz for uninterrupted course videos, coding exercises, and feedback directly from experts in the industry. Now, when does the compiler need these hints? It needs them in a few cases. Here's an example, one example. I'll give you two, and they really cover pretty much everything. Here's a function. It's called longest to name, and it takes two names, which are two references to some data. Well, again, we're using string slices here, not strings. So these aren't owned values. There's some data out there. We don't own it. We're just referring to it. And there's name 1 is doing this, and name 2 is doing this. And how long that reference is valid, we don't know. The compiler does know that the reference is going to be valid for the duration of this function, but it doesn't know outside of that function how long these references are valid, how long it might be till the data is overwritten and all other references become invalid. So if we're returning a string here, or a reference, a new reference to the same data, because if name 1 is longest, then we're going to return that. If name 2 is longest, we're going to return that. The compiler doesn't know how long this returned reference should live. Should it live as long as name 1? Should it live as long as name 2? There's no way to know because we don't know until we're running which one it's going to be, which data it's going to refer to. So in this case, you'll get an error that says missing lifetime specifier. I think in this case, it will put it here. It will say you expected a named lifetime parameter. So here's how it would look with lifetimes, and I'll give you a more formatted example. We specify the lifetime for the function. We have to, just like we include generic types here, every generic that the function is going to possibly involve, same with lifetimes. In these angle brackets, we say this function is going to deal with these lifetimes. And we specify the lifetime of the two incoming references, name 1 and name 2. They live this long. It's just some time period A. It doesn't matter what that time period is because this function doesn't care. And then we say the returned reference will also live for time period A, thus hinting to the compiler, you don't need to worry about the fact that name 1 or name 2 might expire because the thing that we're returning is going to live the same length. So whenever they expire, the thing we're returning is going to expire, and there won't be any invalid dangling references around. We're hinting that to the compiler. And this is one of the main cases. I'm going to go back to this version, same code. This is one of the main cases where lifetime specifiers are necessary, and it's because there are multiple input references, and the output reference is one of those, and we don't know until runtime. Until the program is running, we don't know if it's going to be name 1 or name 2. The compiler has no idea, so the compiler has to cover its bases and make sure that the reference that we're returning, the final name, lives as long as the references that came in. Otherwise, the reference that we're returning will be pointing to something that might have been overwritten and might be invalid now. We don't want that. So for memory safety reasons, the compiler will not let you do this without lifetime specifiers, where you basically guarantee to the compiler that, hey, this thing you're going to give back to me, this reference, it's not going to go bad. And this is already starting to get a little complex, especially if you've come from a language that doesn't need to do any kind of memory reference dangling pointer management or anything like that. And the only reason I'm showing you is that you will run into this, especially when we're dealing with classes or structs in Rust. The other example of where lifetime specifiers are needed are when you have references in a struct. And the struct, again, is Rust's class, basically. You implement code on it, it's like a class. And so we use it a lot. Contracts are often classes. In Cosmwasm, we don't have to deal with contracts as though they're classes, but sometimes we do. And you'll see generics and lifetimes coming in for everything. That won't happen in this example, but eventually you will run into one where the whole contract has a generic lifetime and a generic type attached to it. And so here we have a reference that is a component of the struct. And we have to tell the compiler that the struct will not outlive the reference it holds. We haven't instantiated the struct yet. The compiler doesn't know the scope of the struct. When we create the slice, the sum slice struct, we instantiate it, and then we provide it a reference. We say, hey, in yourself, refer to this data right here. Like this refers to some other data that is unknown, right? Some other, it's called value by convention. Some other value that is, who knows how long it will last. So right now, Rust is concerned, the compiler is concerned that I'm going to create a new slice or a new sum slice rather, create a new sum slice. And I'm going to provide some reference here, create a reference to some value. And then the value is going to go bad. The reference is going to become, go out of scope. It's going to become invalid while some slice is still around. And we don't want that. We want this reference. If it goes invalid, then the struct needs to also be invalid. And so we'll see, hey, expected a named lifetime parameter. So we need to come in and add the lifetime parameter just like we did for the function and specify that this reference lives that long. So we're telling Rust here, the sum slice struct will live for time A, and this reference called slice will live for time A. So you don't have to worry about an invalid reference here where we have a sum slice struct that's living while the reference that it's holding has become invalid. And when we implement code on the sum slice struct, we'll have to do the same thing. We might actually refer to the lifetime somewhere in the code. But this is implementing for lifetime A, code on sum slice lifetime A. So again, lifetimes are needed in that first example where functions are returning references and they have multiple inputs. If there was just one input, Rust could have figured it out. If I was taking in a string, slice, a reference, and then just returning a reference that was based on it, that modified it or sliced it up or something, then Rust would understand lifetime of this and lifetime of that is the same. But since there were multiple references and we don't know which one, we have to actually explicitly give it lifetimes. And structs with references. Like I just showed you, if a struct holds a reference inside, then it needs to have a lifetime specifier. Again, it's so much easier in most contexts to just ignore this. Give your struct a string. It might be a little less efficient depending on what you're doing. And you can just ignore all of this stuff, right? Just ignore it. And sometimes when you're dealing with lifetime problems, this is the way to go. It's just more readable, faster, more maintainable to use owned values rather than references when you're making structs. But sometimes you want them or you have to use them, and sometimes you'll see them in reference contracts and so on. And then other complex reference relationships where in your code, not necessarily in a function body, but inside your code, you have multiple input references that maybe aren't parameters, and they're creating another reference. You might have to use them. You surely noticed that this looks like generics, right? If we had this, it looks about the same. Generics are the same kind of idea. There's some thing that's not exactly specified, just like a lifetime is some amount of time that's the same whenever this is referred to. So just like a lifetime A, it's always the same time, even though we don't necessarily know what that time is. And T, it's always the same type, even though we don't necessarily know what that type is. So what if you need both? Well, then you use this kind of format where you list your lifetimes and generics here, comma separated, and then your generics also can have lifetimes. So here we have a sum slice, and it's not necessarily this, right? I shouldn't even call it some slice anymore. I should call it some reference. We have some reference. It's not necessarily a string slice. It could be a reference to something else. And since it's a reference, I have to tell the compiler that, hey, this reference won't, or rather this struct won't outlive this reference. And I do that by specifying that whatever this type is, it's lifetime A, and up here that we're dealing with lifetime A and type T. And then we get this kind of structure whenever we implement, where we're using type T, we're free to use it as a reference in here. Actually, I think this needs to be this. Yeah, it does. If we're returning a reference here, then we'll need to have a lifetime specifier. That's the whole point. So even though I'm not too scared of lifetimes, I forgot to do that here. And this is getting a little complicated, right? You can understand that this means like the time the thing lives, and it's just the same everywhere. But what if we have like this kind of nonsense? I mean, look at this. We've got a struct implementation that relies on lifetime A, and then we have this compare and return function that deals with lifetime B and C, and we have self, which lasts for lifetime A, and some other thing, right? Some other thing that lasts for lifetime B, because maybe it doesn't have the same lifetime. And then we're returning a thing that lasts for lifetime C, where we are guaranteed that A is at least as long as C, and B is at least as long as C. This is kind of a mess. You could run into problems and you wouldn't really know what was going on. You'd try to match up it's just a mess. So remember, I said use owned when you can, avoid lifetimes. Look at this. This is a little complex. This is maddening. If you just use the thing and not a reference to it, if you can, and you don't use a reference to it, you just use an owned value, then everything becomes a lot simpler. Yes, we still have the generics, but we don't have these lifetimes. And while lifetimes might be manageable here, when we have this compare and return, look at how much more manageable this looks than this nonsense, right? So you can get used to lifetimes. Lifetimes can be fine, but I mean, I'm literally, by owning the T, I get rid of so much nonsense throughout when I do this. Just by one simple change where my struct has a thing instead of a reference to the thing. So if you have to use references, you want to use references for some reason, get ready to deal with some lifetime nonsense. Otherwise, do the owned thing. Own the thing. Don't have ampersand T here, just have T. So I wanted you to understand lifetimes because sometimes you'll have to use them, and you'll definitely see them out and about in the wild, including in smart contracts, as people try to coax some more efficiency out of their smart contracts by using references rather than copying and owning values all over the place. As you get more comfortable with lifetimes, feel free to use them a little more. For now, avoid them, or they'll give you some headache. But if you want to learn more, there's plenty of materials, examples, quizzes in the interactive Rust book, and the other links available at heretolearn.xyz/lifetimes, or if you're already on the platform, in the text associated with this video. Go ahead and poke around. I'm not going to insist that you master these. I don't expect you to see custom lifetimes in the exercises in this course, but you should at least be aware of how to work with them and how to understand what's going on when you encounter them in the wild. And you'll be one step closer to being a Rust smart contract engineer. Now, this video has exceeded its lifetime for sure, so my editor is going to hate me. I'm going to check out, and we will talk to you in the next one. Ciao. Ciao. What the hell? Whatever. Ciao. Ciao it is.